Paper, Information Systems. Section A, System Architecture, 40 marks. 1 question, what are the essential characteristics of cloud computing? 4 marks, answer, the essential characteristics of cloud computing, as defined by NIST, National Institute of Standards and Technology, are 1. On-demand self-service, consumers can unilaterally provision computing capabilities, such as server time and network storage, as needed automatically without requiring human interaction with each service provider. 2. Broad network access, capabilities are available over the network and accessed through standard mechanisms that promote use by heterogeneous thin or thick client platforms, example mobile phones, laptops, and workstations. 3. Resource pooling, the provider's computing resources are pooled to serve multiple consumers using a multi-tenant model, with different physical and virtual resources dynamically assigned and reassigned according to consumer demand. Examples of resources include storage, processing, memory, and network bandwidth. 4. Rapid elasticity, capabilities can be elastically provisioned and released, in some cases automatically, to scale rapidly outward and inward commensurate with demand. To the consumer, the capabilities available for provisioning often appear to be unlimited and can be appropriated in any quantity at any time. 5. Measured service, cloud systems automatically control and optimize resource use by leveraging a metering capability at some level of abstraction appropriate to the type of service, example storage, processing, bandwidth, and active user accounts. Resource usage can be monitored, controlled, and reported, providing transparency for both the provider and consumer. 2. Question, how many types of deployment models cloud? 4 marks, answer, there are 4 main types of cloud deployment models. 1. Public cloud, the cloud infrastructure is provisioned for open use by the general public. It may be owned, managed, and operated by a business, academic, or government organization, or some combination of them. It exists on the premises of the cloud provider. 2. Private cloud, the cloud infrastructure is provisioned for exclusive use by a single organization comprising multiple consumers, example business units. It may be owned, managed, and operated by the organization, a third party, or some combination of them, and it may exist on or off premises. 3. Community cloud, the cloud infrastructure is provisioned for exclusive use by a specific community of consumers from organizations that have shared concerns, example mission, security requirements, policy, and compliance considerations. May be owned, managed, and operated by one or more of the organizations in the community, a third party, or some combination of them, and it may exist on or off premises. 4. Hybrid cloud, the cloud infrastructure is a composition of 2 or more distinct cloud infrastructures, private, community, or public, that remain unique entities, but are bound together by standardized or proprietary technology that enables data and application portability, example cloud bursting for load balancing between clouds. 3. Question, describe about the different guided medias. 4 marks, answer, guided media, also known as wired media, are transmission media that use a physical conductor to guide electromagnetic waves. 1. Twisted pair cable. Description, consists of pairs of insulated copper wires twisted together. Twisting reduces electromagnetic interference, EMI, from external sources and cross-talk between adjacent pairs. Types. Unshielded twisted pair, UTP, most common for Ethernet, relatively inexpensive, and easy to install. Shielded twisted pair, STP has an extra foil or braid shielding to further reduce noise and interference, but is more expensive and harder to install. Use Ethernet LANs, 10 Mbps to 10 Gbps, telephone lines. 2 coaxial cable. Description: consists of a central copper conductor surrounded by an insulating layer, a metallic shield, braid or foil, and an outer insulating jacket. The shield provides excellent resistance to ME. Use cable TV networks, older Ethernet, 10-base-2, 10-base-5, and long-distance telephone transmission. 3. Fiber optic cable. Description: transmits data as light pulses through thin strands of glass or plastic fiber. It offers extremely high bandwidth, long-distance transmission, and complete immunity to electromagnetic interference. Types. Single-mode fiber, SMF, has a very small core, allowing only one path for light, suitable for extremely long distances and high bandwidth. Multi-mode fiber, MMF, has a larger core, allowing multiple light paths, suitable for shorter distances within buildings or campuses. Use high-speed backbone networks, internet infrastructure, FTTH, fiber to the home, data centers. By wireless communication. 4 marks. Answer: wireless communication refers to the transfer of information between two or more points without the use of an electrical conductor or physical connection. Instead, it uses electromagnetic waves, such as radio waves, microwaves, and infrared, to transmit data through the air or space. This allows for communication over distances where it is impractical, impossible, or undesirable to use cables, providing flexibility and mobility. The aspects of wireless communication include: no physical medium. Unlike wired communication, it does not rely on cables or wires to transmit signals. Electromagnetic waves. Data is transmitted using various forms of electromagnetic radiation. Mobility. It enables devices to communicate while moving, providing greater flexibility. Broadcast nature. Signals are often broadcast over a wide area, which can make them susceptible to interference and interception, requiring security measures. Examples: Wi-Fi, Bluetooth, cellular networks, 2G, 3G, 4G, 5G, satellite communication, cordless phones, GPS. 5 Question: List 2:02 Advantages and 2:02 Disadvantages of fiber optics cable. 4 marks. Answer: advantages of fiber optic cable. 1. High bandwidth and data capacity. Fiber optic cables can transmit an enormous amount of data at very high speeds over long distances, far exceeding copper cables. 2. Immunity to electromagnetic interference, ME. Since data is transmitted as light pulses, fiber optic cables are not affected by electromagnetic noise, radio frequency interference, or crosstalk, making them ideal for noisy environments. 3. Longer transmission distances. Signals can travel much further without needing to be regenerated or boosted, reducing the need for repeaters. 4. Security. It is much harder to tap into fiber optic cables without detection, making them more secure than copper cables. 5. Smaller size and lighter weight. Fiber optic cables are thinner and lighter than copper cables, saving space and making installation easier in conduits. Disadvantages of fiber optic cable. 1. Higher installation cost. The initial cost of fiber optic cable, connectors, and specialized installation equipment, example fusion splicers, is generally higher than copper cable. 2. Fragility and installation difficulty. Fiber optic strands are made of glass and are more fragile than copper wires, requiring careful handling and specialized skills for installation and termination. Bending them too sharply can cause breakage. 3. Requires specialized equipment. Connecting and testing fiber optic cables requires specific and often expensive tools and equipment, example optical power meters, OTDRs, fusion splicers. 4. Repair complexity. Repairing a damaged fiber optic cable typically involves precise splicing techniques, which can be more time-consuming and costly than repairing a copper cable. Next question, list 303 factors on which data rate depends. 4 marks. Answer, 3 factors on which data rate, or bandwidth, depends are 1. Bandwidth of the medium, the range of frequencies a transmission medium can carry. Wider bandwidth allows for a higher data rate. For example, fiber optic cables have much higher bandwidth than twisted pair cables. 2. Signal-to-noise ratio, SNR, the ratio of the strength of the signal to the strength of the in the channel. A higher SNR allows for more reliable transmission at higher data rates without errors. Shannon's law directly relates channel capacity to bandwidth and SNR. 3. Encoding scheme/modulation technique, the method used to convert digital data into analog signals, or different states of a signal. More sophisticated encoding techniques, example QAM, OFDM, can pack more bits per signal unit, baud, thus increasing the data rate. Transmission power, higher transmission power can sometimes improve the signal-to-noise ratio over a given distance, potentially supporting a higher data rate, though there are limits due to regulations and interference. 5. Error rate, or BER, bit error rate. A higher acceptable error rate might allow for a higher raw data rate, but at the cost of more retransmissions. Conversely, to maintain a low error rate, the data rate might need to be reduced in noisy channels. 7. Question, what is an object server in client-server environment? 4 marks. Answer, in a client-server environment, an object server, also known as an object request broker or ORB in some distributed object systems like Corba, is a server-side component that manages and provides access to distributed objects. Its primary role is to serve client requests for methods or services offered by these objects. Here's a breakdown of its functions. Object management, it hosts and manages the life cycle of distributed objects. This includes creating, destroying, and maintaining the state of these objects. Request handling, when a client application needs to interact with a distributed object, it sends a request to the object server. The object server receives this request. Method invocation, the object server locates the target object and invokes the requested method on that object. Serialization/deserialization, it handles the serialization of method parameters from the client and the deserialization of return values/results back to the client, converting them into a format suitable for network transmission. Transparency, it aims to provide location transparency, meaning the client does not need to know the physical location of the object it is interacting with, the object server handles the routing. Middleware, object servers are a form of middleware that facilitates communication and interaction between clients and distributed objects, often in heterogeneous environments. Example, in a system where an employee object exists on a server. A client application might send a request to the object server to invoke the getSalary method on a specific employee object. The object server finds that object, calls the method, and returns the salary to the client. 8. Question, what are the two broad classes of middleware in client-server environment? 4 marks. Answer: the two broad classes of middleware in a client-server environment are 1. Transactional middleware, or data access middleware. Focus: primarily concerned with managing and ensuring the integrity of data transactions between clients and databases or other data sources. Functionality: provides features like connection pooling, distributed transaction management, ensuring ACID properties across multiple resources, and data access APIs, example ODBC, JDBC. Database connectivity, ODBC, JDBC, transaction processing monitors, TPMs, like CICS, Tuxedo. 2. Message-oriented middleware, MOM/asynchronous middleware. Focus: facilitates asynchronous communication between disparate applications or components by sending messages rather than direct procedure calls. Functionality: provides message queues, publish/subscribe mechanisms, reliable message delivery, and often ensures guaranteed delivery even if the receiver is temporarily unavailable. Examples: message queues, example RabbitMQ, Apache Kafka, IBM MQ, Enterprise Service Buses, ESBs, Web Services, SOAP/REST. 9. Question: what are the 5 major technologies that can be used to create client/server applications in client-server environment? 4 marks. Answer: 5 major technologies that can be used to create client/server applications are 1. Web technologies, HTML, CSS, JavaScript, web frameworks. Web browsers running HTML, CSS, and JavaScript. Server, backend languages, example Node.js, Python/Django, Ruby on Rails, PHP, Java/Spring, .NET, exposing APIs, RESTful or GraphQL, to the client. Mechanism, HTTP/HTTPS communication. 2. Object-oriented technologies, example Java RMI, Corba, .NET remoting. Client, objects in one application. Server, objects in another application. Direct object-to-object communication, remote method invocation, allowing objects in different processes or machines to interact as if they were local. Example ODBC, JDBC, ADO.NET. Client, applications directly connecting to a database. Server, the database management system, DBMS, itself. Standardized APIs for applications to query, update, and manage data in relational databases. While common, direct client-to-database connections can have security and scalability limitations for complex systems. 4. Message queues/message-oriented middleware, MOM. Client, applications sending messages to a queue. Server, applications consuming messages from a queue. Mechanism, asynchronous message exchange via brokers, example RabbitMQ. Apache Kafka, ActiveMQ. This is excellent for decoupling components, scaling, and handling distributed events. Five. Remote procedure calls, RPC. Client, makes a function call to a remote server. Server, executes the function and returns the result. Mechanism, allows a program to cause a procedure, subroutine, to execute in a different address space, usually on a remote computer, without the programmer explicitly coding the remote interaction. Examples include gRPC, XML-RPC, and earlier forms like SunRPC. 10 Question: What is public cloud and private cloud? 4 marks. Answer. Public cloud. Definition: cloud infrastructure provisioned for open use by the general public. It's owned, managed, and operated by a third-party cloud provider, example Amazon Web Services, AWS, Microsoft Azure, Google Cloud Platform. Characteristics: multi-tenant environment, resources shared among many users, high scalability, pay-as-you-go pricing model, accessible over the internet, no direct control over underlying infrastructure. Benefits: cost-effective, no upfront capital expenditure, high availability, rapid deployment, reduced operational overhead for the user. Drawbacks: less control over data security and compliance, potential for performance variability due to shared resources, vendor lock-in. Private cloud. Definition: cloud infrastructure provisioned for exclusive use by a single organization. It can be managed by the organization itself or by a third party, and it can exist on-premises or off-premises. Characteristics: single-tenant environment, dedicated resources, high level of control over infrastructure and security, customizable to specific organizational needs. Benefits: enhanced security and compliance, greater control over data and infrastructure, predictable performance, suitable for sensitive data and strict regulatory requirements. Drawbacks: higher upfront capital expenditure and ongoing operational costs, requires internal IT expertise to manage, less scalable compared to public clouds. Section B, Operating Systems, 40 marks. 1 Question: why are user-level threads packages generally cooperatively scheduled? 3 marks. Answer: user-level threads, ULTs, packages are generally cooperatively scheduled because the kernel is unaware of the existence of these threads. The entire process, which contains all the user-level threads, is scheduled by the kernel as a single unit. Since the kernel doesn't see individual ULTs, it cannot preempt one user-level thread and schedule another within the same process. Instead, scheduling decisions among user-level threads are made by a user-level library, the thread library. This library relies on the threads to voluntarily yield control, cooperate, to the scheduler at certain points, example when they perform I/O, call a yield function, or at explicit synchronization points. If a user-level thread does not yield control, it will continue to run until it completes or blocks on an I/O operation, which would block the entire process, including all other user-level threads. 2 Question: describe a sequence. The sequence of steps that occur when a timer interrupt occurs that eventually results in a context switch to another application. 6 marks. Answer: when a timer interrupt occurs, leading to a context switch to another application, the following sequence of steps typically takes place. 1 Hardware interrupt: the CPU's timer hardware reaches its programmed count and generates an electrical signal, an interrupt. 2 CPU saves minimal context: the CPU immediately stops its current execution and automatically saves a minimal set of the currently running process's CPU registers, example program counter, stack pointer, program status word, onto the kernel stack of that process. This is done by hardware. 3 Jump to interrupt service routine, ISR: the CPU loads the address of the timer. Interrupt service routine, ISR, from the interrupt vector table and jumps to execute it. This ISR is part of the operating system kernel. 4 Kernel handles interrupt. The ISR begins execution in kernel mode. It identifies the source of the interrupt, the timer. Then invokes the operating system scheduler. 5 Scheduler invocation and decision. The scheduler checks if the time slice for the currently running process has expired. On its scheduling algorithm, example round robin, it decides which process should run next. If the current process's time slice is over or a higher priority process is ready, a context switch is initiated. 6. Full context save. For current process, if a context switch is needed, the operating system kernel performs a full save of the state of the currently running process. This includes saving all remaining CPU registers, general purpose registers, floating point registers, etc., the process's page table base register, and other process-specific information, like open files, signal masks, into the process's process control block, PCB. 7. Context load. For new process, the operating system kernel then retrieves the saved state, the context, of the next scheduled process from its PCB. 8. CPU restores context. The CPU loads the saved registers, program counter, stack pointer, general purpose registers, etc. of the new process from its PCB. It also updates the memory management unit, MMU, with the new process's page table base register. 9. Return from interrupt/resume execution. The CPU executes a return from interrupt instruction. This switches the CPU back to user mode and starts executing the instructions of the newly loaded process from where it was last preempted. 3. Question. Context switching between two threads of execution within the operating system is usually performed by a small assembly language function. In general terms, what does this small function do internally? 6 marks. Answer. A small assembly language function used for context switching between two threads within the same process, or sometimes between kernel threads, primarily performs the following internal steps. 1. Save current thread's context. It saves the CPU's current register values, example general purpose registers, segment registers, stack pointer, program counter, into the thread control block, TCB, of the currently running thread. This captures the exact point where the thread was interrupted. Crucially, it updates the stack pointer to point to the saved context in the TCB or a dedicated kernel stack area for that thread. 2. Load next thread's context. It retrieves the saved register values, program counter, stack pointer, and other registers, from the TCB of the next thread to be executed. It sets the CPU's registers to these loaded values. 3. Jump to next thread's execution point. Finally, it adjusts the program counter, and potentially the stack pointer, to point to the instruction where the new thread was last suspended. This effectively resumes the execution of the new thread. In essence, the assembly function's core task is to swap the CPU's register set and stack pointer from the outgoing thread to the incoming thread, enabling seamless continuation of execution for the new thread. This must be done at a very low level in assembly to directly manipulate CPU registers and avoid higher level language overhead, ensuring efficiency and atomicity. Question. What is a race condition? Give an example. 4 marks. Answer. A race condition is a situation that occurs when multiple threads or processes attempt to access and modify the same shared data concurrently, and the final outcome of the execution. Specific order in which these accesses occur. Since the order of execution is not guaranteed, the result can be unpredictable and potentially incorrect, leading to software bugs that are often difficult to detect and debug. Example, consider two threads, thread A and thread B, both trying to increment a shared global variable counter, which is initially 0. Shared variable, int counter equals 0. Thread A's operations. 1. Read counter, value is 0, 2. Increment counter by 1, result is 1, 3. Write counter, value becomes 1. Thread B's operations. 1 read counter, value is 0, 2. Increment counter by 1, result is 1, 3. Write counter, value becomes 1. Scenario 1, no race condition, ideal. 1 thread A reads counter, 0, 2. Thread A increments counter, 1, 3. Thread A writes counter, 1, 4. Thread B reads counter, 1, 5. Thread B increments counter, 2, 6. Thread B writes counter, 2, expected result, counter is 2. Scenario 2, race condition, problematic. 1 thread A reads counter, 0, 2. Thread B reads counter, 0, / both threads read the old value before A writes. 3 thread A increments counter, 1, 4. Thread B increments counter, 1, 5. Thread A writes counter, 1, 6. Thread B writes counter, 1, / B overwrites A's update. Actual result, counter is 1. In scenario 2, due to the interleaved execution, the final value of counter is incorrect because the update by thread A was lost. This unpredictable outcome based on timing is a race condition. 5 Question, what is a critical region? How do they relate to controlling access to shared resources? 5 marks, answer, a critical region, or critical section, is a segment of code in a multi-threaded or multi-process program where shared resources, like shared variables, files, or hardware devices, are accessed or modified. Only one thread or process should be allowed to execute within its critical region at any given time to prevent race conditions and ensure data consistency. Relation to controlling access to shared resources. Critical regions are fundamental to controlling access to shared resources for the following reasons. 1. Ensuring mutual exclusion. The primary goal of a critical region is to enforce mutual exclusion. This means that if one thread or process is executing in its critical region, no other thread or process can be executing in its critical region with respect to the same shared resource. This prevents concurrent, conflicting modifications. 2. Preventing race conditions. By ensuring mutual exclusion, critical regions eliminate race conditions. If multiple threads were to access and modify a shared resource outside a critical region, their interleaved operations could lead to unpredictable and incorrect results. Encapsulating these operations within a critical region guarantees that they occur atomically, as an indivisible unit, from the perspective of other processes. 3. Maintaining data integrity. When shared data is protected by critical regions, it ensures that the data remains consistent and uncorrupted. Without this protection, partial updates or simultaneous conflicting updates could leave the data in an invalid state. 4. Synchronization mechanisms. Critical regions are typically protected by synchronization mechanisms such as mutexes, semaphores, or locks. Before entering a critical region, a thread acquires the lock. Upon exiting, it releases the lock. If another thread tries to enter while the lock is held, it will be blocked until the lock is released. In summary, critical regions are designated areas of code where shared resources are accessed, and their strict enforcement through mutual exclusion is essential for maintaining data integrity and preventing the adverse effects of concurrent access. 6. Question, what are 3 requirements of any solution to the critical sections problem? Why are the requirements needed? 5 marks, answer, any valid solution to the critical section problem must satisfy 3 essential requirements. 1. Mutual exclusion requirement. If a process is executing in its critical section, then no other process is allowed to be executing in its critical section. Why needed? This is the most fundamental requirement. Without mutual exclusion, multiple processes could simultaneously modify shared data, leading to race conditions and inconsistent results. It ensures that critical operations on shared resources are atomic. 2. Progress. Requirement: if no process is executing in its critical section and some processes want to enter their critical sections, then only those processes that are not executing in their remainder sections can participate in deciding which process will enter its critical section next. This selection cannot be postponed indefinitely. Why needed? This requirement ensures that the system doesn't get stuck or deadlocked. If a process exits its critical section, and there are other processes waiting to enter, one of them must eventually be allowed to enter. It prevents situations where processes are endlessly waiting or where a process is indefinitely blocked even when the critical section is free. 3. Bounded waiting. Requirement: there exists a bound on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. Needed: this requirement prevents starvation. Without bounded waiting, it's possible for a process to repeatedly lose the race to enter the critical section, even if it's continuously requesting access. Bounded waiting guarantees that every process that wants to enter its critical section will eventually get a chance to do so within a finite amount of time, preventing indefinite postponement. 7. Question: why is turn passing a poor solution to the critical sections problem? 5 marks. Answer: turn passing, specifically, strict alternation or Peterson's algorithm variants that use a turn variable, is often considered a poor solution to the critical sections problem primarily because it violates the progress requirement, leading to inefficiency and potential starvation. Here's why it's a poor solution. 1. Violation of progress, busy waiting/strict alternation. In a strict turn-passing solution, like a simplified Peterson's algorithm for two processes where turn dictates who can enter next, if it's process A's turn, but process A is in its non-critical section, remainder section, or has completed its work and doesn't need to enter its critical section, process B, even if it wants to enter its critical section, cannot proceed until process A takes its turn and passes it. This leads to busy waiting where a process might repeatedly check a flag or turn variable, consuming CPU cycles unnecessarily while waiting for its turn, even if the critical section is currently free. Example: if process A finishes its critical work and process B constantly needs to access the critical section, process B still has to wait for process A to take its turn and then pass it, even if process A has nothing to do in its critical section. 2. Inefficiency, busy waiting. The active waiting, busy waiting, wastes CPU cycles that could be used for other productive tasks or for other processes. This is especially problematic on single-core systems or when the critical section is frequently available. 3. Limited scalability, strict turn-passing solutions are generally difficult to scale beyond 2 processes and become cumbersome and inefficient as the number of processes increases. Logic for managing turns among many processes quickly becomes complex. While turn-passing solutions can achieve mutual exclusion and bounded waiting, in some forms like Peterson's algorithm, their fundamental flaw in violating the progress requirement makes them impractical for real-world concurrent programming. Modern synchronization primitives, like mutexes, semaphores, use blocking mechanisms instead of busy waiting to address this. 8. Question: interrupt disabling and enabling is a common approach to implementing mutual exclusion. What are its advantages and disadvantages? 4 marks. Answer: interrupt disabling and enabling, often referred to as simply disabling interrupts, is a method to achieve mutual exclusion by preventing the CPU from responding to interrupts during a critical section. If interrupts are disabled, no other process or thread, including those triggered by timer interrupts for context switching, can gain control of the CPU, effectively ensuring that the critical section executes atomically. Advantages: 1. Simplicity. Conceptually, it's very straightforward to implement. You simply add instructions to disable interrupts before the critical section and enable them after. 2. Guaranteed mutual exclusion. On a single processor system, disabling interrupts absolutely guarantees mutual exclusion because no other code, including interrupt handlers or scheduler, can preempt the running process. 3. Low overhead. In specific contexts for very short critical sections, the overhead of disabling and enabling interrupts can be less than acquiring and releasing a software lock, especially if the lock mechanism itself involves complex operations. Disadvantages. 1. Not feasible in user mode. Modern operating systems typically do not allow user mode programs to disable interrupts directly for security and stability reasons. Only the kernel, privileged mode, can do this. If a user program could disable interrupts, it could halt the entire system. 2. Performance impact/responsiveness issues. Disabling interrupts for extended periods can severely degrade system performance and responsiveness. Important system events, like timer interrupts, I/O completion interrupts, would be delayed, potentially leading to lost data, dropped packets, or an unresponsive user interface. Real-time guarantees in systems that require them. 3. Does not work on multiprocessor systems. On a multiprocessor system, disabling interrupts on one CPU does not prevent other CPUs from executing their critical sections simultaneously. Each CPU would need its own mechanism to ensure mutual exclusion across all CPUs, making simple interrupt disabling ineffective for global shared resources. 4. Potential for starvation/deadlock. If not managed carefully, if a process in its critical section, with interrupts disabled, enters an infinite loop or crashes, interrupts will remain disabled, effectively freezing the entire system. 5. Complexity with nested critical sections. Managing interrupt enabling/disabling. 4. Nested critical sections can become complex and error-prone. Due to these significant disadvantages, interrupt disabling is generally reserved for very short, kernel-level critical sections, example updating kernel data structures, and is not a practical or safe solution for general-purpose mutual exclusion in user-level applications or multiprocessor environments. Section C, Project Management and Legal Regulations, 20 marks. 1. Question: define the following terms. A. Project, 1 mark. B. Software Project Manager, 1 mark. Answer: A project. A project is a temporary endeavor undertaken to create a unique product, service, or result. It has a definite beginning and end, and is typically constrained by scope, time, cost, and resources. B. Software Project Manager. A software project manager is a professional responsible for planning, executing, and closing software projects. They oversee the entire software development lifecycle, manage teams, resources, budgets, and risks, and ensure that the project is delivered on time, within budget, and meets the specified requirements. 2. Question: software project management comprises of a number of activities, which contains planning of project, deciding scope of software product, estimation of cost in various terms, scheduling of tasks and events, and resource management. A. What are the activities that are carried out during project scope management activities? 4 marks. Answer: A. Activities carried out during project scope management activities. Project scope management involves defining and controlling what is and is not included in the project. The key activities include: 1. Plan scope management, defining how the project scope will be defined, validated, and controlled. This involves creating a scope management plan. 2. Collect requirements, eliciting, documenting, and managing stakeholders' needs and requirements to meet project objectives. This includes functional and non-functional requirements. 3. Define scope, developing a detailed description of the project and product. This activity takes the requirements and turns them into a comprehensive scope statement. 4. Create WBS, work breakdown structure, decomposing the major project deliverables and project work into smaller, more manageable components. This provides a hierarchical structure of the work to be done. 5. Validate scope, formalizing acceptance of the completed project deliverables by the relevant stakeholders. This ensures that the deliverables meet the agreed upon requirements. 6. Control scope, monitoring the status of the project and product scope and managing changes to the scope baseline. This involves preventing scope creep and ensuring that any changes are properly approved. B. Explain what is usually estimated during project estimation phase, 8 marks. Answer: during the project estimation phase, the following are usually estimated. 1. Effort, person hours/days/months. This is the amount of work required to complete a task or the entire project, typically measured in units of labor, example 500 person hours. It's the most fundamental estimate as other estimates often derive from it. 2. Cost, budget. This is the monetary expense required to complete the project. It includes labor costs, derived from effort and rates, material costs, hardware, software licenses, travel expenses, training, and other direct and indirect costs. 3. Schedule, duration/timeline. This is the amount of time it will take to complete the project, usually expressed in calendar days, weeks, or months. It depends on effort, resource availability, dependencies between tasks, and concurrent activities. 4. Resources, human, hardware, software. Human resources, the number and type of personnel, example senior developers, QA engineers, designers, needed for the project. Hardware resources, specific computing equipment, servers, networking devices, etc. required. Software resources, development tools, operating systems, databases, third-party libraries, and other software licenses. 5. Risk, while not a direct estimate of a quantity, the estimation phase often includes identifying potential risks, technical, operational, financial, market risks, and assessing their probability and impact. This influences contingency planning and buffer estimates. 6. Quality, although difficult to quantify precisely, the estimation phase might consider the level of quality required and how it will influence effort and time, example more testing, more refactoring implies more effort. 7. Scope, indirectly. While scope is defined, the estimation process often refines the understanding of the scope and helps identify areas where it might be ambiguous or require more detail, indirectly estimating the work involved in clarifying it. C. Discuss 2 types of project estimation techniques, 2 marks. Answer: 2 types of project estimation techniques are 1. Expert judgment/analogous estimation. Description: this technique relies on the knowledge and experience of experts or data from similar past projects to estimate the current project's parameters, effort, cost, duration. It's often used when there is limited detailed information available. How it works: experts, individuals or groups, leverage their domain knowledge, historical data, and intuition to make informed guesses. Analogous estimation compares the current project to a past, similar project, and scales the estimates based on known differences. Pros: quick, simple, useful in early project phases. Cons: can be highly inaccurate if experts are biased or the comparison project is not truly analogous. 2. Parametric estimation. Description: this technique uses a mathematical model or algorithm based on historical data and project parameters, example lines of code, number of features, function points, to calculate estimates. How it works: it involves identifying a relationship between a project's characteristics and its cost, effort, or duration. For example, if a module with 100 function points typically takes 200 person days, then a module with 150 function points might be estimated to take 300 person days. Pros: can be more accurate than expert judgment if historical data is reliable and the parameters are quantifiable. It's objective and scalable. Cons: requires good historical data, and the accuracy depends on the validity of the parameters and the underlying model. Less effective for unique or novel projects. Other techniques include three-point estimation, PERT, bottom-up estimation, and top-down estimation. 3 question, what are the activities that are carried out during project scheduling? 4 marks. Answer, during project scheduling, the following activities are typically carried out. 1. Define activities, identifying and documenting the specific tasks or work packages that need to be performed to produce the project deliverables. This often comes from the work breakdown structure, WBS. 2. Sequence activities, identifying and documenting the logical relationships, dependencies between project activities. This determines the order in which activities must be performed, example finish to start, start to start. 3. Estimate activity durations, approximating the number of work periods, example hours, days, weeks, needed to complete individual activities with estimated resources. This often involves using estimation techniques. 4. Develop schedule, integrating the defined activities, their sequences, estimated durations, and resource requirements to create the project schedule model, example Gantt chart, network diagram. This involves applying scheduling methods like critical path method, resource leveling, and schedule compression. 5. Control schedule, monitoring the status of project activities to update project progress and manage changes to the schedule baseline. This includes tracking actual progress against the plan, analyzing variances, and taking corrective actions.